Okay, so we're happy to have Celeste Damiani, who will tell us about generalizations of Hecke algebras from loop braid groups.
Thank you very much. Thank you for inviting me. I'm going to talk about a joint work with Paul Martin and Eric Roll about generalization of Hecke algebras that come from generalization of braid groups called loop braid groups. And in fact, I'm not really going to talk about this work. I'm going to talk more about the motivation behind. So it's going to be more of a story of how we got there. So I will start with taking things a bit from far and with some behind the scenes, which are not very, I know this is a representation theory seminar. This is not going to be very representation theory, the motivation. The motivation comes entirely from topology and lies in motion groups. So let's take M to be an m-dimensional manifold and an unorientable submanifold in the interior of M. For the moment, we will not be very formal, just try to get ideas. I'm going to omit a lot of technicalities just to pass through what it is that we have to think about. So the motion group of N in M is the group of continuous, first, a motion is just a continuous transformation of M that brings the submanifold N back to its original position after moving inside M. So this concept was defined by Dam in 1962, who was a PhD student of Fox and was working on generalization of braid groups. How can we see braid groups? Well, points moving around the disk. Okay, let's move it up to other dimensions like this. And then the Burau took it again in 1982 to work on motions of other kind of spaces rather than just points in disks. So we can compose motions, and we can say when they are equivalent. So we have a nice group structure, and we call this the motion group of N in M, which encodes the distinct ways of moving N into M, as we saw, so that at the end of the motion, N has returned to its starting positions. So we can see this as the fundamental group of the homeomorphisms with compact support of N with respect to the homeomorphisms of the pair M and N, always with compact support, taking the identity as point. So let's unpack a little bit this to see hands-on what our things are doing. A motion of N in M, we said is an ambient isotopy. Let's call it Ft of X, such that at the moment 0, f of 0 is the identity of the big space M. And at the moment 1, at the end of our motion, N has gone back to itself globally. So maybe if N had different connected components, they could have permutated among them. Okay. So we say that a motion is stationary for N.
So I'm sorry, could you not at the end have ended up with a non-trivial diffeomorphism or homeomorphism of N? Are you saying it becomes the identity homomorphism, or what's the statement? What does F1 N equals N mean?
So F is just an ambient isotopy. It starts from the identity and it ends in something that is not necessarily the identity on the whole of M, but it will have globally preserved the submanifold.
Okay, but it might have mapped N to itself in some non-trivial way, yes?
Yes.
Okay.
So we say that a motion is stationary for N if Ft of N is always N for all time. So for example, we have here a trefoil, let's imagine it in R3, and if we just slide it along itself, then you have there the little movie with the pink dot that moves around, then we see that N is staying at its place for the whole motion, but it's actually moving. So we say that to ambient isotopies are equivalent if the composition of the inverse with the first with the other one is a stationary motion. And we can define alternatively the motion group of M and N as the motions of N in M quotiented by this equivalence relation, which is an equivalence relation. An example, not surprising since that was the inspiration, is the braid group, where we take M to be the disk and N to be P, a set of endpoints in the interior of the disk. A little recap, I don't know what's the background here. I imagine that most people are familiar with the braid group, but just in case, just to be all on the same page. Sorry. The braid group has the very important property that it can be defined in many equivalent different ways. We can see it in many different contexts. So for example, as a motion group, and actually we can translate it looking at the longest sequence of homotopy groups, we can see that the motion group as the pi1 that we defined is isotopic to the mapping class group of the disk with unmarked points. So that we will consider as a unique definition. And I think that in these days, it's more common to work with the mapping class groups. So one definition is the mapping class group of a disk with unmarked points. Then we can see it a la Artin as curves in the disk times the interval I, as you can see in the picture there. Braid groups can be defined as groups of automorphisms of the free group Fn that have the following properties that we see down here, so that every generator of the free group is sent to the conjugate by element in the free group of another generator. And the second condition that we want is that the composition of all the generators is preserved. Moreover, we can introduce it as an abstract presented group with the Artin presentation here. This is not the only known presentation of the braid group, but it's the more common. And we can write it also diagrammatically by indicating every generator as a diagram, and then writing the relations as a sort of braid randomized motions with the pictures. And finally, we can see it as the fundamental group of the configuration space of endpoints in a disk. So let's move, now that we have recollected the whole picture, let's move to another example of motion group, the loop braid group. So the loop braid group can be defined as the motion group or also as the mapping class group of B3, the 3 ball, with Cn and n-trivial link in its interior, where we ask that the homomorphisms preserve orientation both on B3 and Cn. So we have a big space. It's a ball, we have some topological circles inside, and we let them move along some homeomorphism. And we just ask that along the movement, well, if they flip, so the orientation on the co-orientation changes, then maybe they have to flip again, but at the end of the homomorphism, they have to go back with the same orientation that they start. Then we can define loop braid groups as the group.
Sorry, what does n-trivial mean?
Sorry, that's a bit compact and thought for not theory people. It's a trivial link with n components. So we mean n topological circles.
Thank you.
You're welcome, sorry. Then we can see the loop braid group in a way that maybe it's more proper for an algebra seminar as the group of automorphisms of the free group on n generators that are such that each generator is sent to the conjugate of another generator. Remark that this is the exact same condition that we had for the braid group, but we don't ask for the second condition. We don't need the product of generators to be preserved. This definition of loop braid groups which weren't called loop braid group to start with, was introduced by Anna Sabushkina in 1996. She found a presentation for these groups that came back in the literature with another name in another field by Fenriman and Rourke, and this allows us to define the loop braid group also as an abstractly presented group that has the presentation that you roughly see here. You see that you have a set of generators that are like, we would think of them like the braid generators, and another set of generators that we will think of them as permutation generators. So we will have a bunch of relations that I will show you in detail later, because I know that everyone loves to see a long list of relations. But for the moment, I will spare you that. Just think that there are some relations that are the braid group relations, another set of relations that are relations of the symmetric group, and then some mixed relations that tell us how these generators interact. Moreover, as for the braid group, we can associate an elementary diagram to every generator and write the relations in terms of diagrams. And in this form, these groups appeared in the literature with the name welded braid groups. So for every sigma generators, we will associate these classical crossings, such as the braid ones. And for every row generator, we will associate these dot crossings. Then we can define loop braid groups as the fundamental group of the configuration space of n circles on parallel planes in R3. And here, when I say circles, I actually mean Euclidean round circles that can become smaller but remain round. And it's quite an impressive result by Brendel and Archer to see that this group is isomorphic to the group of smooth topological circles. So here we imagine that the main moves that we can have during a path in this fundamental group are moves where two circles pass one into the other. And these correspond to the sigma I generators that we saw in the presentation. And the other elementary move that we can think of is when two circles permute, change position. And this we associate to the row generators. Finally, we can think of loop braid groups as braided annuli, so S1 times I in the in R4, in a four-dimensional space. So here I have a picture that is highly illegal because it's a two-dimensional projection of a three-dimensional thing, which actually lives in R4. But you can see it as a sort of movie where you start in B3 and you just have circles. And at each slice, you only have, in this case, 3 circles that live in a whole B3, not in a plane. Each slice is a three-dimensional space. And we have that all these definitions are equivalent, and we know how to pass from one formalism to the other, which is, it looks kind of obvious when we see those next to the braid groups, and we could have imagined that things work like that. But actually, these objects existed in the literature for quite a long time without often people working on one meaning realizing that their thing is actually isomorphic to the one that their neighbors were working on. So now that we connected all these things and we know how to translate in different languages, this opened quite a big space to consider a problem in one formalism and use these groups as we use braid groups, translate our problem to another formalism and maybe see if there we have more tools. So maybe you have never heard about loop braid groups, but as I said, they appeared in literature with other names a lot. So maybe you heard them with one of these other nomenclatures. When you hear about braid permutation groups and groups of flying rings and basis conjugating automorphisms, we are all talking about some isomorphic version of these groups. So now that we know our protagonists, we can move on to the motivation of this particular work. So I will start with the dream we had. And the inspiration were Iwahori-Hecke algebras. So to define Iwahori-Hecke algebras, where you have R an integral domain and T a unit in R, you can start with the braid group. You can do other things, but this is the standard way for braid, not people where we're not as comfortable with often with the algebraic side. Start with our braid group. There we are at home. And then you do the group algebra of Bn and you quotient it by a quadratic relation, usually a deformation of the one that you see here. Then what happens here is that you can consider the homomorphism from Bn to our quotiented algebra that sends the generator sigma I into the class of sigma I in our new object. And what you can say here, it's already that we can represent any element in this definition of the Iwahori-Hecke algebra by a linear combination of braid diagrams. So once you think about this, you can see this quadratic relation here as a sort of skin relation. And also, if you want to study representations of these two objects, you soon realize that they are very closely linked because representations of this Iwahori-Hecke algebra are equivalent to the representations of Bn, for which the images of Bn satisfy the quadratic relation that we put here. So why is this important in knot theory? Well, every knot can be represented as a closed braid by Alexander theorem. And the other way around, we have Markov theorem that tells us when two braids have isotopic closures as knots. In this sense, an R-valued link invariant is equivalent to a function from the tower of all the braid groups that here I indicated with B infinite into R that are invariant under Markov moves, which are the moves among braids that give you equivalent knots. This kind of invariants are called Markov traces, and this is the path that led to polynomials. So this great breakthrough in knot theory that we all know about, and a lot of work has stemmed through there trying to see what other invariants we can find. Moreover, for those more interested in the links with physics of all this history, I'm not an expert there, but my co-authors are, you have all the root of supersymmetric invariants. And for this, I will refer to work of Paul Martin, Deguchi, and Kaufman and Saller. Something else that has been done in the literature a lot is to try to reverse engineer from not polynomial invariants back to some kind of finitely generated algebra or some kind of algebra. So for example, the Berman, Wenzel, Murakami algebras have been obtained, I think, with this kind of process. And this is just an example. There's a lot of work also in this sense. Something else that needs to be noted about Hecke algebras is that they have a well understood representation theory. There is a reference that was for a seminar with knot theory people, but I guess that in this context, you're more proficient than me about this. So if we put the loop braid group there in the middle instead of the braid group. Can we define a loop-Hecke algebra, loop-Hecke-like algebra, something like this? The first question that we need to ask is, how do we want it to be? What characteristics do we want it to be? So let's think of Hecke algebra characteristics. For once, it's finite dimensional. Then, not only it's finite dimensional, but we know it's a phi R module of rank and factorial. Just to say the same concept a lot of times, it has a basis that is indexed on permutations. So we know a basis. Knowing the basis is what allows you somehow the computation of John's polynomial. And then there are a lot of other characteristics. We will mention in particular that when our parameter is equal to 1, then the group algebra is the one of the symmetric group Sn, and when our domain has characteristic 0 and is generic, then again, the Hecke algebra is isomorphic to the group algebra of the symmetric group. Then when K is a field, we know that the Hecke algebras are semi-simple, except for some values of T. Then, as we said, they have a very well understood representation theory over a field in characteristic 0. And there are a lot of other properties that I will not talk about in connection with physics and the Young-Baxter's equations field. So we have to ask ourselves if we can, what is important that our loop-Hecke-like algebra preserves? What do we want of this? To be finite dimensional would be already something. So in the very naive definition that we could give just by plugging LBN in there and keeping the same relation, would this be finite dimensional? To know, it's useful to know exactly what are the relations in the loop braid group. So as I told you at the beginning when I was giving the definitions, here we have the braid relations. So if two generators are on strands or tubes in this case, or have indices that are far enough, then they commute. Then we have the classical Reidemeister 3-like relation where sigma I plus 1, sigma I is equal to sigma I plus 1, sigma I plus 1. Then for the row generators, we have the symmetric group relations where we have rho I and rho j commuting where they are on indexes that are far enough. Rho I squared is 1. We have this kind of involution, and if you think of it as the movement of the circles when you saw the definition in terms of configuration spaces, it means that if we change the circles once and then we change the circles back, we have actually the same configuration. We have come back somehow. And well, the third symmetric relations, like for the row, we have rho, like for the sigma, we have rho I plus 1, rho I equal to rho I plus 1, rho I plus 1. And then the interesting part are the mixed relations. So the first one gives us no surprise. When we have generators that happen on different parts of our braid where the indices are far enough, they commute. And then we have these two others where we say that sigma I rho I plus 1 rho I is equal to rho I plus 1 rho I sigma I plus 1, meaning that if I take a classical crossing, I can slide it through two welded crossing, and this is an equivalent, this is a relation. And one could think, well, then we draw all the possible variations of Reidemeister 3. This works still when for this other relation, where we have rho I passing under a strand. So rho I, sigma I plus 1, sigma I equal to sigma I plus 1, sigma I, rho I plus 1. See this one slides under. But then, if we try to write the symmetric one, so where we have the welded crossing that has to pass over a strand, this one does not hold in our group. To see why this makes sense and why it's not just an arbitrary, I will take one relation and not the other, it's useful to write these braids in terms of automorphisms of the free group. Just follow the generators where they go, and one sees that they go to different places. Simply, this one does not hold. For those that are familiar with the virtual braids have the same sets of generators, and the relations arrive up to this one here, the one with one classical crossing and two welded, or in that concept, virtual ones. This other relation does not hold for virtual braid groups. So we were talking about finite dimension.
Sorry, can I just ask a quick question? So the sigma i's act in the usual way on the free group, and the rows just act by swapping generators. Is that correct?
Yes.
Okay.
Sorry, I didn't say that, but they
But you implied it.
inside two permutations, automorphisms.
Yeah.
So to see, let's see what kind of elements we have here and how we can act with our relations. So we have all this arsenal plus this one here. Well, unfortunately, I can write sigma I rho I, and I have no relation to break it. Sigma I rho I, sigma I, sigma I rho I, sigma I rho I, and go on as much as I want. But I have nothing that breaks me this kind of words. So no, we are unhappy. This first naive attempt is not finite dimensional. We need to kill these kind of words. Where do we take tools to do this? Well, for studying Hecke algebras, we saw that knowing something about braid representations was a useful thing. So what do we know about representations of loop braid groups? Well, let's first see what we know about braid groups. We have Burau representation is the most historically studied representation of braid group, and is the representation obtained by sending one elementary generator of the braid group into this matrix. And this is not a faithful representation. This has been proved in several steps by many authors, and it has been quite a long road to get there. For many, many years, there was a hope that it would be faithful and that we would know that the braid groups were linear because of it. However, then we have the Bigelow-Kramer-Lorentz representation, which is faithful and tells us that the braid group is definitely linear. We have a whole family of local representations coming from Ian-Baxter equation. And, okay. And then if we want to push forward our paradigm of taking the braid groups and sending it into an algebra that has generators and relation and going further on that road, we would get to Temperlely-Lieb algebras. So we can talk about representations of braid groups that are linked to representation of Temperlely-Lieb algebras, Berman, Murakami-Wenzel algebras, and so on. Not to go into the unitary representations and other representations that are studied more from a physics point of view. So which one of those have a side into counterpart into loop break groups. We look which ones extend. When I say that a representation extend, I mean that it is still a representation when we send the braid generators to the same thing and the permutation generator to something that makes sense for permutations. So for example, I didn't even mention it in the previous slide, but of course, for braid groups, we have Artin representation, sending the braids into the automorphisms with the conditions that we saw. And we have an Artin-like representation also for loop braid groups in the same way, just because we can define them as that kind of automorphisms of the free group. Then Burau representation, well, we have an extended Burau representation, which is obtained simply by sending permutation generators into permutation matrices, where you have your 0, 1, 1, 0 block matrix in there. And they respect on the relations, so we are kind of happy with that. Then Lawrence-Kramer-Bigelow, it's a bit controversial. So you will find in the literature that it does not extend to loop break groups. However, when people say that it does not extend to a loop break group, they refer by a work of Bardakov that proved that they do not extend combinatorially, meaning doing the naive attempt, which is the first that we have to do, of sending the matrices of the braids elements to the braid element matrix as they were, and then plug in some permutation matrices, exactly as it's been done for Burau. In that case, we have no extension. When we try to verify the relations, we see that they are not verified. However, Lawrence-Kramer-Bigelow representation has an homological construction, which has not been attempted with loop break groups. So maybe we should not just take the matrices, but look what the matrices represent. Can we define homologically Lawrence-Kramer-Bigelow on loop break groups? It becomes more complicated, more intricate. So that's, I suppose, is the reason why it's not been done yet, but there is still hope.
Is there an expectation that that representation will be faithful? I mean, I guess it's too far to worry about that, but.
It's another topic on which we have hope, and it's a bit a religious thing.
Okay.
Do we want to think that the loop break groups are linear? We don't know. They have a lot in common with braid groups, though.
Yes.
So that's what we know. And about local representation, it depends on what we are talking about. This is a partial overview. There is a good state of the art of representations of loop break groups in a recent preprint. I think it's still a preprint, I'm not sure, about Bellingeri and Soulier. That work exactly on representations of loop break groups. So let's go back to our attempt of loop-Hecke algebra. So, and let's fix a couple of things. We will take our domain to be C and a parameter in C, because remember that we are not here to play with those. We want polynomial invariants or some knotted objects. And we remark that this particular relation that is used for Hecke algebras is satisfied by Burau matrices. In particular, we can see it as a sort of coming from the Alexander polynomial. If we write the Alexander polynomial, the Conway-Alexander way, so with the skin relations, we can do some rewriting games with the skin relation to obtain this. So it's as if we started for Alexander polynomial, we went back to the algebra level, and what we find up there, it's Hecke. Alexander polynomial is just the knot theory word for Burau representation. So, and for loop break groups, we have Burau. Why don't we try to do the same thing? So remember that our issue was with this kind of word where we have the same index, sigma I, rho I, sigma I. So let's take the extended Burau matrices for this minimal word Si sigma I rho I. This would be the matrices Si rho I and Ri Si. Let's try just to play with the matrices and see what happens. Well, what happens is that they satisfy these two, this is annoying here, these two relations down here. There's nothing particular about that. The way we found it was just really multiplying, looking at the matrix, multiplying the matrices, looking at it, trying to rewrite it somehow in a different way. It might be not the most, so these relations, we found them like this in a kind of heuristical way. It might be not the best relations to consider. There might be other ways to write them. However, we found two and we tested them. We did our quotient with all these relations, and we could prove that this loop-Hecke algebra is finite dimensional. The proof is again not flying very high. It's a matter of combinatorics and rewriting words. So with on the loop braid relations, with the additional quadratic relations and the original quadratic relation, we can write other relations to solve terms where, for example, in lower degree, just let's take LB3. You see here I have row 2, sigma 2, row 2. We are taking words where we have more than one generator that has a high level index. So in LB3, you would have generate indices 1 and 2. And we thought, can we write them in such a way there is only one index that is in the maximal level? So we could write all these words. And then once we had this, we could prove with an induction that the vector subspace of LHN spanned by 1 and the sigma I or I generators can be rewritten by words in the lower level. So sorry, the LHN plus 1, I get meddled with the indices, can be written by words in the lower level, on one side on one other, and in the middle, you will always only have one generator in the higher level. So this is a long and convoluted way to say that you start writing words and eventually they all simplify down. And you end up with something that is a spanning set, a generating set for LHN. Unfortunately, it will not be a basis. So one thing that we can say about this is that the dimension is bigger than the image of the extended Burau representation. So this is a good news. We have something that is bigger than Burau. And yet we have something that is not crazy huge, probably. We know the dimension of these algebras for low levels because we computed it with computer programs. So with our kind of naive approach of just plugging in some relations, we found we fell on an algebra which was of an interesting dimension. One interesting thing is that if we specialize the parameter t, the dimension can go a bit up instead of just with Hecke. The most that could happen is that it went down to the symmetric group. Here it can go up. First news about it is that we could see that it's not semi-simple. Initially, we took it as a bad news because it's different from Hecke algebras. However, in studying 3+1 TQFTs, the ones that are not trivial usually come from non-semi-simplicity. So maybe it's not a bad news. Another property is that we can define a local representation related to Burau using Rittenberg representation. And we will call this the loop Burau-Rittenberg algebra. And we will fall asleep while we say this name. We hope not. Very, very condensed here. The way we define this loop Burau-Rittenberg algebra is by matrices and relations. So we take the algebra generated by these matrices here that look, we say, oh, that's Burau. No, look at the minus t down here. It's slightly different than Burau. And the matrices S will be like the matrices R, where we specialize t equal 1. And the way we obtain the representation is by sending generator sigma I into this composition here and rho I into this composition here. So this box is very annoying, sorry. Properties that we could see about LBRN algebras is that we could see, study their structure, and it's independent with respect to the parameter t, except when t is equal 1. And the thing that interests us most is that when t squared is not 1, then the loop-Hecke algebras are isomorphic to these matrices generated algebras. So up to n equals 7, we know the structures of loop-Hecke algebras because they are the same as loop Burau-Rittenberg algebras. So our conjecture is this always true? Are loop-Hecke algebras always isomorphic to loop-Rittenberg algebras? And in that case, we would know a lot about the structure of loop-Hecke algebras. However, we need some smarter tool to prove this. Up to 7, what we did was check it via computer computation. To go further, we need some idea of why this might be true and how do we prove it. But this is really, I think, very, very promising. Yeah, I'm sorry for the little hearts that I draw there. I got a bit carried away by the conjecture. So from there, what can come next? From a knot theory point of view, what could be interesting is using these algebras as we used Hecke algebras to find topological invariants of surfaces in R4. For instance, loop braid groups have knotted counterparts that are ribbon torus links, knotted tori in a 4-dimensional space, which when they are very tame, we can sort of imagine like the elegant picture that I draw here. Then, can we do this process also for other quotients, or for other motion groups? For instance, there are not many motion groups for which we know a presentation, but there are some. We, Bellingeri and Mudan, I think, gave a presentation for necklace braid group. So groups where you have one big circle and other circles that are chained on it, and they can move, they can frog hop among them, but they will always be along the same circle. And those have a relation with circular braid groups. There is a presentation, not a beautiful one, for H trivial links, meaning trivial links where you have some Hopf components and some trivial components. For other knots moving into space, it looks rather complicated to find presentations. But yes, then there's a lot that has to be tried. Deborah Goldsmith gave some presentations, again, not short, very workable presentations for certain kinds of knots in S3. So here we are mostly working in R3 and R4. There's some work to be done to see if it's possible to translate her work. But in that case, we could have quite a family of motion groups. From which one of those can we abstract Hecke algebra? We know that in the literature there are a lot of generalization of Hecke algebras, but my impression is that they are obtained either combinatorially, looking at the presentation and thinking what else you can do, how we can change that presentation, or with algebraic motivations. I'm not sure that there's a lot done starting from the motivation of, I have this object moving into space. Can I attach an algebra to it? And then the last interesting question, at least that I could think of while I was writing this, but I'm sure that there are many other questions, is can we use non-simplicity as a feature for using loop Hecke algebras in some context? And I think, yeah, I sped up a little bit, so it's early, but I will finish here.
Thank you very much. Thanks, Celeste. Are there questions for Celeste? So do you have, so I mean, Hecke algebras and quantum groups, they are related by some sort of Weyl duality. Do you have an idea of what's going on in the quantum group side? Or, okay.
No. It's one of the many ends of this story that we didn't even start looking into.
Mm-hmm.
So, sorry, I feel I've been asking too many questions, so I don't know if I should
not at
give
all.
other people a chance. So one question is, I mean, since you wrote down this, okay, so you found some presentation and by writing generators and relations, and I guess the conjecture is that away from this point where t is plus or minus 1, this thing that you call the Burau-Rittenberg representation, that's a faithful representation. Is that right?
Yes, I would say so, yes.
Okay, so the point is that it's a faithful representation of the algebra that you defined.
Well, not necessarily of the loop Hecke, because we don't know. I mean,
that's
yes,
the conjecture.
If the conjecture hold, yes, sorry.
I mean,
yes.
No, but in fact, that's exactly the conjecture. You write down an algebra, you write down a representation, and you would like to claim that this representation is faithful.
Yes.
That's
I mean, I didn't.
But...
Oh, yes. What?
I hope I mean, it's just a sort of, I don't know, in representation.
The conjecture is that, yes.
Yeah, okay. Okay, fine.
Can I
go ahead?
Can I ask, just because we're talking about faithfulness here, so are you talking about faithfulness in the sense that the generators are sent to different different elements, or faithfulness when you talk about a representation of an algebra to be faithful? That means that the whole mapping is injected
into the endomorphisms. Yeah. That's exactly
right. Yeah.
So if these are infinite dimensional, then the representations would have to be infinite.
No, but they're not. The Hecke algebra is finite dimensional. It's mapping into n by n matrices.
Right. But if some of the other infinite dimensional, if we're looking for representations of those.
Well, we stuck with this quotient because it's not infinite dimensional. It is finite dimensional. So, and for instance, we know, I don't know, I have to read the numbers because I never remember the dimensions like that. But so for
They
n
better
equals
not
3,
be more than n squared, right?
yeah, but for n3, for n equals 3, so if we have only 3 strands tubes on our braids, the dimension would be 15. So okay, it's not huge. Then it goes up fast, of course, but yeah.
So I'm sorry. So maybe I missed something. Why is it 15? I thought this representation that you wrote down, it's inside n by n matrices, or is it n plus 1 by n matrices?
I'm going back a bit to yes, this one here. Take just n equal 3. So the only generators that you have here are
Okay.
sigma 2, row 1, row 2.
Yes.
For this, in the naive way of just writing words that are of this form,
Yes.
one can write up to, I don't remember if it's 21 or 23 words.
Yeah, I'm sorry.
Some other space of matrices, we saw that they are not independent. So this is just, we would just obtain generating set, not a basis. But then with the computer, we checked that this would be, there would be 15 independent.
Yeah, so let me apologize. So I misunderstood. So I always, since I'm not in this area, I get confused between the Burau representation and the reduced Burau representation. So this is why I thought it was in n by n matrices, but of course it's in n plus 1 by n plus 1 matrices.
Yes, yes.
Okay, so for n equals 3, the biggest number should be 16. But you found something of size 15.
The space of the extended Burau matrices, we should be a
16.
16?
Yeah, it's 4 by 4 matrices, so it's 16 dimensional. And your algebra is 15.
Sorry. No,
am I wrong?
9, because Burau matrices are 3 by 3. The reduced one would be a 2 by 2.
Oh, so then I missed completely. So in this representation that you write, I thought you were writing down everything as a matrix of a certain size.
Let me find Burau matrices. Okay. I didn't put the indices here.
Yes.
Can I write somewhere? No, I cannot write. I don't have somewhere to write. No, but for example, in LB3, you would send sigma I into sigma 1 into this block at the top, and then just have a 1 underneath.
Okay, but just what is the size of the matrix? So you're writing extended Burau.
LBN would be n by n.
N by n, yes? And so after you look at the algebra that they generate, it's sitting inside n squared dimension.
Yes, so if it's 3, the dimension would be 9.
So, but your algebra is dimension 15, so this representation couldn't be faithful. Now I'm confused.
No, it wouldn't be, not with Burau, not with extended Burau. And that extended Burau is not faithful, that we know. I mean, Burau representation for braid groups was not faithful starting from 5, and I think 4 is still unknown, but it was good.
These Bigelow representations which are faithful.
No, but we're talking about Hecke algebras, Burau representations of Hecke algebras.
No. Burau representation is not faithful. Already for n equals 3, it's not faithful.
No, but of the Hecke algebra, it is faithful, right? I mean, it's not faithful for the braid group. I mean, to go to the Hecke algebra, you already made a quotient of the group algebra.
Are you talking about, where is it?
Maybe I'm confused now.
This one. What?
So
I'm not sure.
Yeah, so, okay. So let me just ask, so let's go back to your conjecture. I just want to understand the conjecture, that's all. I don't want to.
Yes.
Okay, where's the conjecture?
So we define, there.
Very good. So we define these matrices, right?
Mhm.
And you are looking at this LBRN algebra, and it's the algebra generated by the RIs and SIs.
Yes, which are not Burau matrices. They are slightly different from Burau matrices. And
Yeah, but that's okay. But so first, when we talk about the algebra, the field of scalars is T and is it's rational functions in T, is it not? What's the dimension that we're talking about? I mean, what's the field?
C, we're always on C. Yes.
But what about T then? T is what's the
a parameter in C.
T is a parameter. Okay, fine. Or formally, we could work in rational functions in T as the field C of T. Okay, right. So what you're writing down are matrices of some fixed size.
Yes.
What is the size? That's what I'm asking.
Well, it's this tensor product of that you can see up here.
Yeah, and it looks like it's n, right? No,
it's inside of a huge tensor product, right?
It's yes.
It's in a huge tensor product. This is what I missed. So what's the ambient dimension?
I'm not sure.
It's probably something like cubic or something almost exponential, right?
Okay. All right. So this I completely missed. So this is exactly what I missed. It's inside some big tensor product. So it's a priori finite dimensional, but it's not n squared or n plus 1 squared or something silly like that. Okay. Yeah, I apologize. I just misunderstood. And so, but the dimensions, they seem to grow like quadratically when you've computed them, or how do they behave?
In the first levels, we have 1, 3, 15, 114, and then it goes to 1170.
Okay. So second question is, did you
we try to plug this number into the sequences. Fine.
Yeah, exactly. And
as usual, the most sensible guess it makes is some kind of transformation of the Catalan numbers.
Yeah.
But I don't even remember what were the suggestion it made, because there was nothing that gives us an idea of what could be a smart basis for this. There was nothing that you was like, that's it. We are going to prove that it's I don't know, something like permutations for Hecke. There was nothing that looked like that.
But it was a known sequence, right? Up to 7, it looked like some known sequence.
It looked like some known sequence.
Okay. All right. So that's usually a clue, right?
Yes.
Especially if you can check if the next one also fits into the sequence.
Yes, but we are not going to prove the general conjecture by.
Of course not. No, but that's good too. Okay, sorry, I'm just I'm interested in Hecke, braid groups and Hecke algebras, and but more from the point of view of affine and double affine. So but this is just some different direction, and it's interesting to figure out.
Thank you.
Are there other questions for Celeste? Okay, let's thank her again. Thank you for the nice talk. Let's stop the recording.